I want to welcome everyone to the DARPA ERI Summit here in Seattle. It's our pleasure to be here, and thank you for coming. I want to tell you a secret. Seattle was the place we selected to have the summit, the ERI Summit, in the year 2020, and unfortunately we were not able to come at that time. But we're thrilled to be here today, and this is, of course, the first in-person summit that we've had since 2019. There are over 1,300 attendees here from government, from academia, and from industry, the commercial sector, both the industrial sector and the defense sector. We're here at the ERI Summit to share challenges together, to talk about some of the advancements and some of the plans that we have in the microelectronics industry. So over the next 3 days, we're going to talk about a once-in-a-lifetime opportunity to reinvent domestic microelectronics manufacture. We're going to get perspectives from microelectronics leaders, including, just to name drop a bit, Congressman Adam Smith, the Honorable Heidi Shyu, Dr. Lori Locascio, Steve Welby, Bill Daly, Mark Papermaster, and many others. And while our focus is going to be on ERI 2.0, we're challenging you to think broadly about the microelectronics revolution that we are tackling together. And now, it's my pleasure to introduce our opening session, and it begins with a distinguished speaker whose experience in the world of microelectronics is really unparalleled. It's my pleasure to welcome Intel CEO, Mr. Pat Gelsinger. A minute. Pat, a few words. Pat joined the microelectronics industry at the age of 18. He quickly became a prominent figure. Throughout his career, he's been an advocate for the importance of technology in semiconductor manufacture. He became the company's CTO in 2001, where he led numerous key technology developments, such as Wi-Fi, USB, Intel Core, and the Intel Xenon processor. Since February of 2021, he served as the Intel CEO, and his focus has been on reestablishing Intel as the global leader in microelectronics manufacture. Ladies and gentlemen, Mr. Pat Gelsinger. Thank you, sir.
Thank you very much. It's a great pleasure to spend some time with this esteemed audience. Obviously, echoing Senator Cantwell's comments, hey, we believe in microelectronics and we believe on rebuilding that leadership in the U.S. and the manufacturing thereof. And, you know, I'd ask each one of you, right, what aspect of your life is not becoming more digital? Name it. You know, your banking, your social, right, your network. What aspect of your job is not becoming more digital? Right? And every aspect is becoming more digital, every mission that you're on, and everything digital runs on semiconductors, right? This is seminally important to what we do, you know, for the future. And, you know, as we think about that, you know, we believe deeply in the public-private partnership. We believe fundamentally that we can and must do work together, you know, to accomplish that. And, you know, as we think about these systems that we're building, these vast distributed systems, you know, the requirements for silicon, the requirements for security, and COVID was a massive wake-up call. We realized all of a sudden we had lost control of the supply chains for these underlying technologies. You know, imagine we're short a $2 semiconductor and we can't ship a $30,000 car or a $15 million jet, right? All of a sudden we realized how fragile our supply chains had become. And we fundamentally, as a company, as we're rebuilding our leadership, you know, we also believe deeply in the partnering with U.S. Government. We see our goals as synergistic with your goals for the future. And we're committed to keeping this magic of silicon alive and supporting those mutual missions. You know, since our founding, Intel has thrived on this relentless pursuit of semiconductor invention and innovation. You know, and I'll say this simple idea of Moore's Law, you know, has been the singular driver of the greatest portion of innovation and wealth creation of the last 50 years. And we see that, you know, we as a company still remain in the thick of it all, if you would. And as I like to say, until the periodic table is exhausted, we ain't finished. And we're going to keep this magic of silicon alive. And under it, I call these 5 superpowers. The first of those is compute. Since the 4004, which we just celebrated this 50th anniversary, everything's becoming a computer. Every light bulb, every light switch, thermostat, right, is becoming a computer, right, associated with it. It's become critical to every program and everything that you do. Second is connectivity. As one of the people who helped to create Wi-Fi when we were cutting the wires for the first time, right? Now everything and everyone is connected. And as you've heard, no comms, no mission, right? How critically important that is. Everything's becoming connected. Infrastructure. We now, right, can essentially build supercomputers in the cloud on a moment's notice. And with edge, we now have seamless, low latency, high performance capabilities that build this cloud to edge infrastructure. We literally have infrastructure at scale. And increasingly with core clouds, hybrid clouds, tactical, disconnected capabilities, we truly have infrastructure at scale. Of course, AI, right? And as you think about the superpower, as I like to say, AI as a field is a little bit over 40 years old. What happened the first 30 years of AI? Nothing. And the last 10 years exploded, right? The algorithms got good enough, the data got large enough, and the compute got big enough, and all of a sudden we can now have software writing software at scale, autonomy, vision, robotics, all of these, providing situational awareness, new capabilities for every, piece of machinery and delivery that we provide. An F-35 pilot in the future, when he takes off, all of his AI-assisted drones are going to, launch in concert with them. Every tank, every soldier in the battlefield, and all of these need more silicon. And sensing. We can now, right, one of my businesses is Mobileye, autonomous vehicles. The high-end cars now have 16 cameras on them in multiple spectrums of light. When you drive, you're hideous. You only have 2 eyeballs. I put 16 in the car, and none of those get distracted by your instant messaging, and they're all learning from everything around. We're now able to sense everything. Unfortunately, my family has a genetic problem with hearing, so I now wear hearing aids. But my hearing aids are now the latest AI-assisted. I'm running a neural network here that does spatial sound and beamforming, right? So my weaknesses become digitally enhanced strengths in the future. We're literally able to sense everything. We know where we are. We see in more places. We hear more things. And if I can get my hearing aid back on, I can hear more things again. And these superpowers enable us to bridge between the analog and digital worlds as never before. When I came back to the company 2.5 years ago, we set out on an aggressive path to rebuild Intel's technology leadership. We said 5 nodes in 4 years. Typically, a node takes 2 years to develop. We said we're going to get 5 of them done in 4 years, right? A tremendously audacious and aggressive path to build. And of these, Intel 7 and 4 are largely finished. Intel 3 goes to production the first part of next year. So we are on track to deliver our 5 nodes in 4 years. And the next big ones are a major new structure in metallurgy, right? We're basically with wafer level assembly with PowerVia, we're essentially building the power delivery network into silicon using big, fat, wonderful IR, favorable metals. And then we flip the wafer over and create a wafer sandwich, right, with a major new advancement in transistors, ribbon FET. And this gives better power, signal delivery. You take all of that power delivery network and you get it out of the signal path because you deliver it from the backside of the silicon. And we're seeing extraordinary benefits from rebuilding the power network and microelectronics and silicon. And this is an area that we're 2+ years ahead of the rest of the industry. And the other thing that comes with Intel 20A and 18A is ribbon FET. And for those of you who've been around transistors for a long time, I will simply call this the perfect transistor, right? Because now you have a fully surrounded gate, right, around the channel of the transistor. No leakage, full control, right, of the device itself, VT optimization, minimized leakage, full performance capability. So a major transistor innovation and a major metallurgy innovation in Intel 20A and 18A. You know, we're committing all of our product line, you know, to take advantage of these. So I'm sort of like, you know, at the, you know, if we're in Vegas at the poker table, we're going all in, right, with all of Intel's revenue, right, to go make these technologies successful, as well as foundry customers, as well as working with government customers as well to make these major innovations on track. We'll be delivering the PDK 0.9 very shortly. That'll become available in the industry. And this combination of 5 nodes in 4 years on track to be leadership process technology on American soil by the end of next year, the commitment I made when we became CEO. And we're on track to accomplish that, and happy to say that beyond those, Intel Next and Intel Next, and beyond that, you know, we're well underway on the advancements that go beyond 20A and 18A. But the other wonderful thing that's happening, and even Gordon Moore predicted this when he wrote his initial paper on Moore's Law, you know, that there will be a day of reckoning, right? You know, where X and Y aren't enough, and we got to go to packaging technologies. And essentially, old silicon stuff is becoming cool new packaging stuff, right? And we're now applying these silicon technologies to advanced packaging. And we're now entering into the advanced packaging era where 2.5D and 3D packages become the new norm. And one of these EMIB, as we call it, you know, it just rolls off your tongue, you know, embedded multi-die interconnect that basically allows us to break the field size of lithography and stitch them together in very high performance active silicon bridges that bring them together. And this is now going into volume production in our server, high performance computing, AI product lines. Another one is what we call foveros, and this is where we actually start stacking, right, multiple pieces of silicon on top of each other. And here's our Meteor Lake chip. And of course, you can see this very carefully, I'm sure, right? But we actually have 4 pieces of silicon stacked into one. 3 die on top of 1 base die, you know, that enables us to deliver more transistors per unit area. And as I call the combination of advanced lithography, advanced packaging, new transistor structure, and new power delivery, those 4 together, Moore's Law is alive and well. But of course, we're just getting started. We're also now innovating with glass substrates. Intel helped to create the organic substrate industry a little bit over 20 years ago. The next step is glass. And for that, glass has better thermal characteristics. It allows us to go to finer bump pitches for it. And the one that really excites me, as you can tell, I don't get excited about this stuff. The one that really excites me is when we go to glass packages, we now get to fully integrate optics. Right, you start doing waveguides directly in the package to bridge between, you know, silicon photonics and optics for the first time at scale. So excitement in the area of packaging technology. But of course, you know, this is just a framing for the many longer-term research things that we're doing together. And as part of the DARPA CHIPS program, the common heterogeneous integration of property reuse strategies, we're building how do we create chiplets and new reusable IP blocks. And essentially, you'll be able to design a chip on each process technology that's optimized for RF, optimized for power delivery, and start combining those together so you're composing an advanced package of chips and chiplets into the future. You know, in this CHIPS program, we're already demonstrating great results, you know, from it, this disaggregation of the platform and being able to put these pieces together. You can lower schedule risk, you can optimize individual technologies, you compose these most advanced components, you know, into these advanced packages, and we're already starting to deliver, you know, examples of this using chiplet standards. Intel's also driving what we call UCIe, somewhat like PCIe was for board standards. UCIe is for chiplet standards as we put these components together. And we're already delivering some of our FPGAs in this way, delivering on an order of magnitude improvement in many of the RF applications that are possible. And another great example, we're part of the PIPES program, Photonics and Package for Extreme Scalability, an area that as we start breaking into some of these most advanced interconnect areas, the role of optics, the picojoule per bit requirements are going to have a major step forward. And as I said, I think glass packages will be one of the key enablers thereof. And fundamentally, as I like to say, Moore's Law alive and well. Right? And God gave us this amazing material called silicon, and there's not much silicon left in silicon. Meaning we put more and more scaffolding of more and more materials into that structure. So continued advancements in new materials, new extreme transistor designs for ultra low voltage operation, new memory structures, using new device types for that, and continued lithography research as well. An area I'm quite excited about is direct write, eliminating EUV entirely and just going to low performance direct E-beam write onto wafer so that every chip is unique in the future. We're also doing joint work in the areas of neuromorphic computing, right? A class of computing that seems very interesting for certain algorithmic and search domains. But the one that I'm really excited to show you is, how many of you have held a quantum computer yet? Okay, here's a quantum computer. Right now, of course, when you see quantum computers, they always look like these big, massive, crazy things. That's because you just got this big honking refrigerator, right? You just got to get to cryogenic temperatures. But don't be fooled. There's no science there, right? Here's the science. So here's a 12-qubit chip built in silicon. And the magic of this, we call it tunnel falls. The magic is being able to use CMOS and silicon to produce qubits. Because if we can do that, if we can show the material structures for cryogenic, below 1 Kelvin, right, such that we can have CMOS-like circuits work, I can build a lot of them, right? Because maybe it takes about 1 million physical qubits to create quantum supremacy. If we can do it in silicon, I'll give you as many qubits as you want. Right? And for that, this is, we're about to tape out our next generation chip. It leverages those billions of dollars that we talked about with Intel 18A, right? And being able to now produce manufacturable qubits, at cryogenic temperatures, right? With cryogenic control circuits for error correction, et cetera. A lot of excitement about what we'll be able to do. And my personal thumb in the air is, by 2030, quantum supremacy is possible at scale. But we have a problem, and Maria mentioned this in her comments, Senator Cantwell, that the world is now critically dependent on semiconductor supply chains that we no longer control. I'll argue that over the last 5 decades, where the oil reserves are has defined geopolitics of the world. Where the supply chains of technology are is more important for the next 5 decades. Let's build them where we want them. And for that, as we see this next surge of innovation and technology, this is part of the reason that we've been so excited to participate in CHIPS Acts and other efforts. And with President Biden, with Secretary Raimondo, with President of the EU, President van der Leyen, 50% by 2030, going from 80% US and Europe in 1990, less than 20% today, back to 50% by the end of the decade. That's the moonshot that we've laid out. And for that, I've been thrilled that I've had a personal role to play in helping to get the CHIPS Act passed in both the US as well as in Europe. Some of these pictures were from the day that we announced our Ohio location, just outside of Columbus, Ohio. And when I stood on stage with President Biden, and I said, today, the Rust Belt ends. Today, the Silicon Heartland begins. You just feel, right, the enthusiasm for manufacturing, reshoring, and rebuilding our technology supply chains, for the future. And for that, we're simply excited about the progress that we've made in a short time since the passage of the CHIPS Act. And we now have submitted our project proposals for our locations in Arizona, in Ohio, Oregon, and New Mexico, 4 sites, Intel has invested and announced investments of over $150 billion on American shores as we rebuild our manufacturing and research capabilities. And this includes modernization of new facilities, the most advanced material research work in the world, quantum research centers, advanced lithographic centers, as well as rebuilding our U.S. semi workforce as well. We're also thrilled to be able to do this in partnership with many of our government allies, the RAMP-C program, Rapid Assurance Microelectronics Prototypes, effort that we've initiated with the U.S. Department of Defense in 2021. Last month we announced an expansion of this program that now includes Northrop Grumman and Boeing are joining the program along with IBM, Microsoft, and NVIDIA, to build these supply chains. We're also the driver of the SHIP program. And the SHIP program, state-of-art heterogeneous integrated packaging, and this has been a fun project for us. As we began the work in 2020, we've now delivered first article solutions from that program for these advanced packaging technologies, and it was just 6 quarters ahead of schedule. Now, how many of you have participated in a program in the defense community that's ahead of schedule and under budget? Sorry, right? I'm sure we'll find some way to spend the money. But, truly making progress to rebuild our long-term research and capabilities in microelectronics and advanced packaging. We're also running the University Shuttle Program. Today we have about 50 universities, about 200 shuttle passengers a year. Every time my team updates me on that program, I said I want it 10x bigger, right? And when we get a 10x bigger, I want it 10x bigger yet, as we scale to rebuild. Because I remember in my own academic, right, when Moses and those programs, that's how I got my start. We need to be building the talent of the future and revitalizing innovation and advanced silicon capabilities for our universities, our startup community, and our advanced defense activities. This is the heart. This is where Silicon Valley began. In summary, we're committed to pushing the boundaries of what is truly possible. This path forward is clear. This partnership of public and private sector. You cannot afford for the defense community to build your own fabs. It is commercially not viable to build them or to keep them modern. You have to leverage what we do in the commercial segment. But we can't be pushing them forward and advance the research efforts as only you have shown over decades to do. It really is this public-private partnership, and joining forces, we truly have the opportunity to restore our innovation, restore our economic capacity and communities. And Intel's committed to be this partner that pushes the very envelope of what is possible in physics. We're committed to the benefits, the opportunities that this brings, not only economically to our nation, but to our national security as well. And we want to build this resilient supply chains that we've created a better world for our children and grandchildren. Thank you very much.